All right, so this is section 10.4. It's over secants and tangents. So when we look at this problem, um, we need to start with, like we always do, some basic words and some definitions. The first is that word secant. And a lot of these definitions are straight out of your book, so most of the time we're going to be reading them as opposed to writing them. So the first word is the word secant, and it's just talking about a line that intersects a circle at exactly 2 points. So that makes this line up here a secant because it contains a chord. So that's our first word. This one is a secant, so we can probably label that. The second word is the word tangent. A tangent is a line that intersects a circle at exactly 1 point. We call that point the point of tangency. So that this point is the point of tangency, right here. And this line is called a tangent, or a tangent line. Tangent. All right, so now that we've got words, what can we do with these things? A tangent line is perpendicular to the radius drawn to the point of contact. Or if a line is perpendicular to the radius at its outer endpoint, then it's considered to be tangent to the circle. So if we know that this point T is a point of tangency, and we know that that TP is a radius, then we know that this is perpendicular. So if it's a point of tangency and a radius to that point of tangency, then we know they're perpendicular. So that's our first fact. And it goes backwards and forwards. So if we know it's a tangent, then we can say that the radius is perpendicular. If we know it's a radius and a point of tangency, then perpendicular, all those good things. So that's our next fact. The two-tangent theorem is the first one that we encounter that we're really going to work with a lot. So let's go back through the things that we know. We know that if this is a point of tangency, let's call it x. And we also know that y, down here, is a point of tangency. Then, those are points of tangency. Then we have right triangles. And since they have radii that are obviously congruent, because all radii of a circle are congruent, and they have this shared hypotenuse, by hypotenuse leg, these two triangles are congruent, and the AX then has to be congruent to AY. The two-tangent theorem is the one that's going to allow us to do that without doing congruent triangles. The two-tangent theorem says that if I have two lines that are tangent to a circle from the same point, then those two lines are congruent. You're not going to have to write it. You're going to have to be able to look at it and know it. I'll say it again. If I know that AX is a line of tangency, and I know that AY is a line of tangency, then I know that AX and AY are congruent by the two-tangent theorem. So that's our next rule. All right. I think that's the only one on that page. Yeah. All right, let's go to the next one. More vocabulary. Tangents in two circles. So think about two circles and how they could be related to one another. The first is that those two circles could be externally tangent. Externally tangent circles are arranged like this. They have a common point, right? That's one point of tangency. That's the place where they touch. And we have another vocabulary word. When we connect the centers of two circles, it's going to be called the line of centers. When we have externally tangent circles, read that phrase again, externally tangent circles. When we have that, then the point of tangency is on the line of centers. My two circles are actually tangent to each other. The point of tangency is on the line of centers. Now, these two circles were externally tangent, right? Each of them on the outside. And can we look at some of the things that we'd be saying? We could be saying that radius PT and radius TQ. To get the sum, we would have segment PQ. So we have lots of things that we could be doing with this. So previously in the chapter, we saw overlapping triangles that had a common chord, right? They looked like this. We had overlapping circles that had a common chord. That's what this guy was. Now we have externally tangent circles. We also have internally tangent circles. Internally tangent. So if we have circle P and circle Q, notice that that line of centers gets extended and the point of tangency is still on the line of centers when our circles touch. So they're considered internally tangent if they just touch on this one spot. Okay, so we talked about when they touch outside. We talked about when they touched inside. Now we need to, and we talked about when they overlap. The last piece we have to talk about is when they aren't tangent to one another, when they're pulled apart or they're separate. What do we see when that happens? What do lines of tangency look like then? If the circles aren't tangent to one another, then they may have common tangents, a line that's tangent to each circle, not necessarily at the same point. So we could have a common internal tangent. So that tangent line, so notice here, this line xy is tangent to circle Q at point y. Line xy is tangent to circle P at point x. And it's called an internal tangent because it's in between the two circles. Or you can think of it as it crosses the line of centers. A common external tangent, like segment, or rather like line AB, does not cross the line of centers. It does not go between the two circles. So as long as you understand all of those words and our two big pieces, that if they are tangents and radii are perpendicular, and the fact that two tangents from the same point are congruent, then you're all set for our problems for today.